Hello and welcome to the MyHeritage webinar series. I'm Jeff Rasmussen, your host, broadcasting to you live from Middleton, Idaho. Today we have Ran Sneer from MyHeritage to teach us about working with DNA segments on MyHeritage. Also with us is you, more than 2,300 of you from 50 countries around the world have registered for today's live webinar, so wherever and whenever you are, so glad to have you with us. A quick note that the complete U.S. Yearbooks collection at MyHeritage is now free through May 23rd, and in addition to it being free, we have used our new in-color technology and have colorized the entire collection. I personally found my own grandmother in her 1950 yearbook and saw for the very first time what she looked like when she was just 16 years old. This is her at the top left and was very exciting to find. Then I glanced at the page on the right and saw a picture of who I thought was me. It looked, well, I knew it couldn't have been me. Then I read the caption and I learned that it was my grandfather. So after today's webinar, head up to myheritage.com/yearbooks and see who you can find. And now I'd like to introduce today's speaker, Ran Sneer. As product manager, Ran is responsible for MyHeritage DNA products. He leads a talented team of developers, QA engineers, and designers to create and optimize DNA users' entire journey from ordering a DNA kit, tracking the kit's progress, receiving results, to leveraging a continually growing suite of features to make the most of the DNA results in genealogical research. Ran, we're going to be doing this just a little bit differently today. Ran is unable to be with us live, and so he actually made the time to pre-record his class just for you, which we will view together in just a few seconds. And then after that, we will have door prizes and go from there. If you're unable, now this technology of viewing this pre-recorded class, it's going to work for 98.8% of those of you watching live. If you're unable to view the video, I would invite you to watch it in its entirety in just a few hours. It will be in the webinar library at familytreewebinars.com. So let's welcome Ran, and here we go.
Thank you, Jeff. It's great to be back here for another webinar. I think it's been something like a month since we did our marathon, which was the last time in which I participated. So it's great to be back. And the topic we're going to discuss today is working with DNA segments on MyHeritage. This is a topic I especially like. I think that there's a lot that you can learn by looking at the DNA segments, the shared segments you have with your DNA matches. And even though some folks think that it's a little bit more advanced or requires a lot of previous or background knowledge, I don't think that's the case. And I think that within few tries or a couple of attempts to look at segments and try to understand the concepts, people can learn a lot from it. So that's why I love this topic, and I'll try to make it as clear as possible. For those who don't know me, my name is Ran Sneer. I'm the product manager for MyHeritage DNA. And let's start. So I usually give some background about genetics and DNA inheritance in each one of my webinars and lectures. But I think that for this specific topic that we're going to discuss today, it's even more important to emphasize some of the terms or to talk about the terminology, make sure that we understand the concepts of how DNA is inherited, because the key to work with your shared segments, with your DNA matches segments, is to understand how this whole thing actually works. So it's not going to be very complicated, I can promise you that. So stick with me and we'll get it through. So each one of us, human beings, we have 23 pairs of chromosomes. The first 22 is what we call autosomal and are the ones that we use on MyHeritage for DNA matching. And the 23rd chromosome is the sex chromosome, X and Y for a male and double X's for females. So today we're going to focus about the autosomal chromosomes, the 22. And as you can see, they are pairs. And the reason that they are pairs is because we inherit each one from a different parent, okay? And we'll talk about that in a second. So these are the chromosomes. Now, another term to know or to be familiar with is what we call a SNP. A SNP, in the very basic way to describe it, is a specific location on the genome. One dot, 1 point on our genome, which contains certain values. So if we'll zoom in, for example, on chromosome 1, which I selected here, we can see that we have these letters running, right? In biology, we use 4 letters for DNA, A, G, C, and T, and we inherit these letters in each one of the SNPs that we look at. So, for example, in this combination right here that it shows, this is, for example, a SNP. And in that SNP, I have one A and one C. One I've inherited from one parent, and the other one from the second parent. We don't know which one. That's the tricky part. And on our genome, there are over 3 billion base pairs, such as this one. But for genealogy, when you take a DNA test and we process your results, we actually end up with about 700,000 such SNPs that we use for DNA matching, ethnicity estimate, etc. And the reason is that because about 99.9% of the DNA between two human beings, any two human beings, will be exactly the same. All right, so we spoke about chromosomes and about SNPs. And a segment is basically just a sequence of SNPs. So if I'll take the G and now the C and the A, and I'll just kind of group them together, so we can say, for example, that this is a DNA segment, okay, which contains 3 SNPs or 3 parts of the SNPs. And these are the segments we use to do our DNA matching. When someone takes a DNA test, whether with us or with another company and uploads to MyHeritage, we take his results and we compare it with all the other DNA data files that we have on MyHeritage. And what we're actually doing when we're doing DNA matching is that we're trying to look for segments or sequences that repeat, that look similar between 2 individuals. They need to be at a certain size, at a certain length, and if it's long enough, like in the example here, we can see the lines that I've highlighted in red. You can see that the same sequence repeat of the GGA, GGGA, GAA, and then what continues over there. And if that looks similar between person A and person B, we say that this is a shared segment between the 2, and they might be related. These segments, we call them IBD, identical by descent, which we believe were inherited from a common ancestor. This sequence is long enough and unique enough so that we decided that our algorithms have identified as a segment that's a segment which potentially was inherited from a common ancestor for these 2 people. Let's talk about inheritance of DNA. And for this, I will use my favorite example of Frank and Molly, which you can see right here. Let's look at chromosome 1 for both of them. And as we mentioned, there are 22 of these. But this is just for the sake of the example, we're going to use chromosome 1. I'm using colors, so I've decided to paint chromosome 1 for Frank in 2 shades of purple, and Molly I'm using orange. Okay, so again, as I explained before, we have pairs of chromosomes. Each one of the chromosomes has is built out of 2 alleles, what we call alleles, one inherited from dad, one inherited from mom. So the good news is Frank and Molly got married and they had a son, Ben. And this is how Ben's chromosome 1 looks like. So you can see now that Ben has, again, a pair of 2 alleles on chromosome 1, as he should, And you can see that he has a mixture of the colors that we see above. So we see Frank's two colors, Frank's two allele represented in the upper allele of Ben, and then Molly's colors, Molly's DNA represented in the bottom allele of Ben. And we'll explain what's going on with the colors in a second. Let's zoom in on what Ben inherited from Frank. Okay. So we can see that what happened here is that Frank contributed some of the DNA he inherited from parent A to Ben up till that point, and then he contributed the remaining of that allele from the second parent, which are actually Ben's paternal grandparents, right? So what happened there, right there in the middle, is what we call a recombination event. It's when the two alleles are switching between one another when a new child is conceived. So Ben actually inherited some DNA from his first grandparent and then some DNA from his second grandparent and ended up with this genetic data. Let's look at what's going on with what he inherited from Molly. So again, Molly has one from mom and one from dad, or Ben's grandparents in this example. And here we can see that two recombination events happened. So we started with grandparent A, then there was a switch to grandparent B, and then again from grandparent A. And these recombination events happen a lot and randomly on the chromosomes when we're conceived. And this is how DNA is inherited. So we saw Ben's DNA. Let's look at another example. So Ben had a sister. Her name is Lisa, as you can see right here. And you can see that Lisa's DNA, again, the same thing happened, right? So Lisa inherited one allele from Frank, her father, and then the other allele was inherited from her mother, Molly, and there were recombination events, but the DNA looks a little bit different, right? Again, these recombination events can happen randomly and many times in each chromosome. So if we'll try and look at what's the similarity of DNA, how much DNA Ben and Lisa have in common, again, just for that one chromosome, you can see that on the right. So you can see the darker purple at the beginning, then there's a stop, they don't share DNA at that point, and then the lighter purple, and the second allele even less, right? You can see that there's a little bit of orange. And if we'll try to look at it, it looks as if there's like almost 50% of shared DNA between Ben and Lisa, right? They share roughly 50%. Let's look at another generation. So Ben got married and Lisa got married and they had kids, and new colors are now part of the game, right? So Lisa married a guy who is represented in the color of green, and Ben married a woman who is represented in the color of blue. And now let's try and see, and you can see that Eric and Julia don't share any DNA on the bottom allele, right? Assuming that the spouses of Ben and Lisa are not related to one another. But you can see that there's a lot of shared DNA on the first allele, the one which still represents the genetic data that came from Frank and Molly's parents, right? Their great grandparents at the moment. And if we look at how much Erica and Julia share, who are first cousins in this case, you can see that it's less than what Ben and Lisa had. Now we're talking about roughly 25% of the shared DNA. And that's exactly how inheritance of DNA works and how we are doing our DNA matches technology, what our algorithms are actually doing. So we're trying to look at the amounts of shared DNA between two individuals, and based on the amount of shared DNA, we can suggest what might be the relationship between these two individuals. So as we saw in the example before, 50% is usually the case for a parent-child match or for siblings. If we jump one generation up, we're already at 25% because every generation, about 50% of the shared DNA is degraded, as we saw in the example before. So now we're talking about the grandparent-grandchild relationship, uncle-niece, maybe. 12.5%, we get even further and further and further and further. So the percentage of shared DNA, amount of shared DNA, which is also represented by centimorgans, which is the value of measurements in genetics, is what helps us determine what the potential relationship could be. And there is a variety of relationships, right? And as the percentage goes down, the variety goes up. So in this example right here, you see myself and my wife and my daughter. And basically what it means when my is matched with someone named Jane Doe, for example, and there's some amount of shared DNA between them, what it actually means is that there is one or more shared segments between them, a sequence of DNA which looks similar, which our algorithms believe that it's an IBD inherited by descent, and therefore contributed or passed down from a common ancestor that the two of them have, right? So in this case, we're talking about my great-grandfather. All right. So now that we know the basic concepts, we can start and talk about the chromosome browsers and what are they, how can we use them, and what benefits they give. So this is my list of DNA matches. And if I choose one of the DNA matches and I want to deep dive, I can go to the Review DNA Match page. Before I do that, let's focus for a second on the DNA match card. So in this example right here, I get a new match. His name is Homer Simpson. And see what we are showing you on MyHeritage. So the area that's currently highlighted is the DNA match quality. In there, you can see the amount of shared DNA, 1.4%, which is actually 102 centimorgans, which translate into 1.4%, how many shared segments we found, and what is the length of the largest segment out of these 10. Based on this information, we are able to say what is the estimated relationship. The estimated relationship that we're showing here, Homer, for example, can be a first cousin twice removed, till a third cousin, and that's a big variety of options, is solely based on the DNA match quality that we just described. So 100 centimorgans, 102 centimorgans, which are 1.4% of shared DNA over 10 shared segments, will fit every one of the relationships within the range of first cousin twice removed to a third cousin. All these options are possible. In the Review DNA Match page, the last component on the page is the Chromosome Browser one-to-one, if you want. What the Chromosome Browser does, what is it first? It's a tool. This tool allows us to visually look at the shared segments that we have with the person that we're currently looking at. So in this example, I'm looking at my cousin Elon, and you can see the 22 chromosomes, shown right here. And the colored areas are the ones in which my DNA is similar to Elon's DNA in those specific locations. These are the shared segments that we have. Okay. So again, it's just a representation. Many people think that the Chromosome Browser is the Holy Grail, just to get the option to look visually and see the nice colors on the website. But it's just a representation of where exactly on the genome you and another person have shared DNA, like in the example I showed at the beginning, which is shown here again. So this is the Chromosome Browser in the Review Match page, which shows you just for one person where you match. Okay. The second Chromosome Browser that we have, which is more useful for, I'd say, a more thorough analysis of your DNA matches, is the one which can be found under Tools in your DNA Results, Tools, and then on the bottom left there, the Chromosome Browser. So if you hit Explore, you will get to this screen. Here you can see yourself. If you're managing DNA kits for more people, you'll have the option to switch there from the Compare drop down above my photo right there. And below it, you will see your list of DNA matches. You have the option to search by a name if you're looking for a specific one. And if not, they are sorted by default by how close they are to you, by the amount of shared DNA. So here we can see my immediate family, my close family. So this chromosome browser, unlike the ones we just discussed, is the one which lets you look at shared segments between one DNA match and up to 7. So you can pull all these people together and see where you share DNA with them. Where do you have shared segments with them? And we'll also explain how that can be helpful. So let's start with an example. So I decided to take 3 DNA matches to start with, Robert, Sandra, and Stephen. So I pull them from the bank at the bottom there, and by clicking on them, they are added. And once I hit compare, I get to a new screen which shows me where I'm sharing DNA with these individuals, right? So at the top there, you see their names. Each one of them is represented in a different color. The one-to-one chromosome browser, which we saw in the review match page, is always in purple because we're always looking at one individual. But in this case, we can look at up to 7 individuals simultaneously. So we are representing each one of the DNA matches you've chosen with a different color. And every DNA match that you'll add will be added with a new line for each one of the chromosomes. So you can see, at first we give you a short glimpse of the DNA match quality you have with each one of them, like we saw for Homer Simpson before. So that's listed above. And then below it, you can actually see where you have shared segments with these individuals. So the first line in each chromosome, represented in red, are the shared segments you have with Robert. In orange, Sandra, and in yellow are the shared segments with Stephen. Of course, the names are random, and the colors can change as well, but each DNA match is represented in a different color to make your life easier. If you scroll to the bottom, you'll see a table view, all right? These collapse, I'll show that in a second, which indicate the information that you saw above in a graphical way. If you'll click on each one of these individuals, a table will open up and you'll be able to see where exactly you share DNA with these people. So with Robert, for example, I can see in the screen capture that I took here, 2 shared segments on chromosome 1 with the start and end location, and the length of that segment, 6.1. I'm skipping the start and end RSIDs, less relevant for this discussion today, and the amount of centimorgans, how long the segment is. Okay. So that's what the chromosome browser looks like. These are the results that you're going to get if you'll try to compare your DNA data with your DNA matches and the different outcomes you can get. One thing I didn't mention yet, and that's because we need to have a little bit, we need to define a term first, which is triangulated segments. And that's really where chromosome browsers and the DNA segments are getting interesting, in my personal opinion. Triangulated segments are shared DNA segments that you and all of the selected DNA matches share with each other, and therefore likely all inherited from a common ancestor. Okay, so, and now simplifying or trying to say it in different words, triangulated segments might be displayed, or we might indicate triangulated segments if you choose 2 or more DNA matches and all of them are matching one another at the same spot, okay, at the same location on the genome. And you are matching them, of course, because they're in your list of DNA matches. And when that happens, when all the people that you've selected to compare their DNA to one another and to yourself are matching in a specific location, that can be a hint that all of you are related through a pair of common ancestors. Let's look at a few examples. So here I have a tree, a family tree, and the 4 people, the 4 cells in color are people who have taken a DNA test, okay? So maybe let's try and see if we can find who would we expect here if we compare them as groups. Who would end up showing that they have triangulated segments, that they are all sharing segments with one another at the same spot. So one group that you might notice is the group of Carol, Alice, and Bob. So they are all descendants of William and Zandra. So very good chances that William and Zandra have passed down DNA to Carol, Alice, and Bob. So Carol, Alice, and Bob will all be DNA matches of one another, and very good chances that they'll have the same segments in the same spot. But there's another group here, which is different, and that's the group of Alice, Bob, and David. So Alice, Bob, and David are common. They also have common ancestors, but these are not William and Zandra. These are Eve and Zelda, at the top right there. So again, Alice and Bob have also inherited DNA from that couple, and David also inherited some DNA from that couple. So that's interesting because Carol and David might not be DNA matches at all, but you can see that Alice and Bob can have triangulated segments with Carol and triangulated segments with David, even though they are not related to one another. Let's start with a few examples. So this is my personal family tree. I'm there at the bottom left. Above me is my father, Raphael, and above him we have my grandparents, Raya and Avram. So I was able to test both myself, my dad, and my grandma. So let's see what happens when I take the three of us and I try to look at the shared DNA that all of us have. So I started by clicking on my father and my grandma. They were added, and I hit compare. And now we can see that there's a lot of DNA we all have in common, right? So with my dad, because I inherited one allele of each chromosome, you can see that the first line is colored all the way through in all of the chromosomes. Because with my dad, I'm sharing one of my allele is similar completely to a combination of my dad's alleles in each one of the chromosomes. With my grandma, that's not the situation. You can see that with my grandma, I share way less DNA. That's also indicated in the amount of shared DNA that you see right there. So with my dad, I share 50% approximately, and with my grandma, 25, because the rest of 25, the remaining 25, I've inherited from my grandpa. Okay? But what's interesting to talk about here is the indication that we show up there for how many triangulated segments were found. And that indication will appear for in any time that you'll choose 2 DNA matches or more. And those triangulated segments, we mark them with that bubble that's surrounding the area where there is a triangulated segment. So in this case right here, what this means in chromosome 2, for example, is that in this specific location, I share DNA with my dad, I share DNA with my grandma, and they are also sharing that DNA in that specific spot. So that's one segment that all of us have in our DNA that is similar, which can hint that we all have a common ancestor. In this case, that's my grandma herself, who contributed her DNA to my grandfather, who then passed it down to me. Let's look at another example. One thing I forgot to mention before is that if you hover over each one of these segments, both the triangulated and the regular shared segments you have with each one of the DNA matches you are looking at, you will get this tooltip showing you the information about that segment. That's the same information that is also provided in the table at the bottom of the page. Right here. Okay, so if there are triangulated segments, first, in my previous example, we looked at the shared segments I had with a specific DNA match that we looked at. Here in this example, because there are 25 triangulated segments between the group of DNA matches I'm currently looking at, we are also surfacing that here. So these segments are the ones that we all have in common. Here's another interesting example. Here I'm comparing my DNA with my grandma, with whom I share 25% DNA, as you can see, and a DNA match of mine, who I don't know who he is, and his name is Jackie. With Jackie, I share roughly 2% of DNA, almost 2%. And something interesting is happening here, which might be confusing in a first look. So while at the top it says that there are no triangulated segments, meaning either, in this case, my grandma Raya is not DNA match of Jackie at all, or they are DNA matches, but the segments that they share are different than the segments that I'm sharing with each one of them, are in different locations, different positions on the genome. When we look at the chart below, we do see overlap in chromosome 1 and chromosome 6, and even in chromosome 2 there, which I didn't circle. So that's weird. How come I share DNA with my grandma on chromosome 1? I share DNA with Jackie on chromosome 1 in what seems to be the same location, but there are no triangulated segments. And the reason that this is happening is because of the two alleles that we have. So here is an example of explanation of what's going on here. So with my grandma, in this specific position, I share my first allele. And with Jackie, I'm sharing my second allele, coming from my other parent. So even though I'm sharing with each one of them, Jackie and my grandma, Rochelle or Raya, are not sharing any DNA at this location at all. And this is why there are no triangulated segments. So it's a good hint. There's a 50% chance that if you see an overlap in a specific location, it is actually a triangulated segment. But use those tips that we give with the bubbles, because we are also checking the connection between the other people that you're comparing, and looking whether they are DNA matches of one another and whether they're sharing DNA at the same spots. So another example for what we just saw, where we see an overlap, is this example right here, where I'm taking my dad and my mom, and I'm comparing the DNA that I share with each one of them. So it looks very colorful, very beautiful. So I have a full line of red, which is my shared DNA with my dad on chromosome 1, and then a full line of orange, which is the shared DNA I have with my mother, but there are no triangulated segments. And the reason is that, exactly in the example that we showed here, I share one complete allele with my grandma and one complete allele with my mom, and one complete allele with my father, but they are not sharing DNA with each other because they are not related. Okay, so we spoke a little bit, we saw some examples. Let's see how the Chromosome Browser can help identify connections, and what's really the power behind looking at shared segments and what they can tell us. So here I have a new DNA match. His name is Gene. I share about 1.2% with him, and there's a wide variety range of possible relationships. So I want to use, and I didn't mention, but it says here that Gene doesn't have a family tree on MyHeritage. So I can't look really at surnames or places or look at this family tree pedigree chart, nothing like that. All I have to do is work with the DNA data that we have. But actually I can take a lot from it. So the way I like to start is by taking one of the parents. All we're trying to do with our DNA matches is try to figure out and understand how we're related to them, right? So in this example right here, I want to see whether Gene is related to me on my maternal side. So I put myself, I add my mom and Gene, and I compare. And the Chromosome Browser tells me that there are no triangulated segments. All right, so I'm going to my family tree, and for now I'm going to rule out the option that Gene is related to me through mom. And I'm going to try with my dad, and here I expect there to be a connection. So I'm comparing now myself, my mom, and Gene. And you can see that there are 7 triangulated segments, which is great. It means probably Gene is related to me on my paternal side. Cool. I'm moving forward, and now, as you've seen before, I had the privilege to test my grandma. So let's see whether me, my grandma, and Gene have triangulated segments. I'm trying to compare, and MyHeritage tells me that there are no triangulated segments. What that hints to me? That hints to me that for now, probably Gene is not related to me through my grandma on the paternal side, but rather through my grandfather. And that's the best way to use the Chromosome Browser is by taking what you can call anchors or DNA matches of yours who you have an identified relationship with, you know how you are related to them, and try to see how DNA match data of how other DNA matches data looks like when you're comparing the 3 of you or the 4 of you. Here's another example. So up till now we've used my father, mother, and grandma, but see how another relative, a little more distant, can help figure out the connection. So this is a story from about 2 years ago, a little bit more than that. One day I received a notification from MyHeritage that I have a new DNA match by the name of Edie Julik, and we share 1.8% of shared DNA, which can end up as being first cousin twice removed to a second cousin twice removed. That's relatively close, in my personal opinion, and I don't know any Edie Julik. I've never heard that name. So I decided to investigate further. I checked my brother, who I've also tested, and you can see that my brother has 3.3% of shared DNA, which is almost double, or way more, let's say. And now the relationship is even, the estimated relationship is even narrower, right? Because I think that in my case it was first cousin till second cousin twice removed. So we were able to narrow down the options. There are less options now if we combine what my brother and me have. I want to stop for a second and explain. A lot of the people are asking, I see a lot of the questions whether it's worth to test siblings because you have your DNA data, so sometimes they won't contribute a lot. In this specific story, for example, my brother contributed a lot, and that also goes back to the beginning of the presentation. So you remember that we said that siblings on average have 50% of shared DNA, in between 37 to 50% full siblings, 37 to 50% of shared DNA, but it's not the same DNA. They inherit different segments. So if we test our siblings, it gives us a better picture. That's all under the assumption that we can test both parents, for example. It gives us more DNA data of our ancestors, right? Because each one of us contributes some more parts, and we get a bigger picture of the DNA. Anyway, moving forward, I went to MyHeritage to look at Edie, and unfortunately, she didn't have a tree on MyHeritage. So that, again, I cannot use the surnames or places, and I have to use only the genetic data that MyHeritage provided about this match. So I went and looked at the shared DNA matches to begin with, because that's the quickest way. And what I can see here is that me and Edie are both matching my mom and her sister, which you can see there at the bottom, in a way higher percentages, as you would expect it to be in a higher generation. So 4.8% for mom and 6.3% for Iris, her sister. Again, an example of how testing siblings can help. So Iris has more similar DNA with Edie than my mom. So we can use that. Okay. Let's look at the family tree and see what we can say up till now. I didn't mention before, but the other two folks here are my daughter, who doesn't contribute much to this research, and my brother Shai, we already discussed. So what do we know? So this is me. So Edie is my match, and she's matching my brother, obviously, and my mom, and my aunt. So this is what I know so far. And the question stands now is whether she's related to me through grandma or grandpa on the maternal line. And luckily, as you can see right there at the bottom right corner, that's my second cousin, Effie. So Effie also took a DNA test. So I can use Effie to try and see whether Edie is also matching her and whether there's a triangulated segment. Effie is related to me through my grandmother line, as you hopefully can see here. And if we'll see a triangulated segment between myself, Effie, and Edie, that can be a good indication that Edie is related to me on my maternal, on my grandma maternal line. So that's exactly what I did. So I pulled in Effie, my second cousin, and Edie. I compared, and I was told that there are no triangulated segments. Okay. So I'm going back, and I'm ruling out the option of Effie, her mom, her grandma, my great-grandparents, and my grandmother. And now the direction I'm pursuing is through my grandfather. My grandfather passed away when I was 3 years old, so I didn't have a chance to test him. And this is what I know so far. This is what I've highlighted. We took a step up in the tree, and here you can see that we ended up with my great-grandparents on my paternal on my maternal grandfather line. The story goes even further. I think I even discussed it in a previous webinar that I gave here, so look it up if you're interested. But we were able to figure out how Edie is related to me, and that's indeed the line. And the fact only by that I had my second cousin Effie test, and me ruling out the option that this is coming from my grandma's line, I was able to look into this direction, and eventually we were able to understand how Edie is related to us. Again, kind of an emotional story. Look it up if you're interested. But Edie is related to me on my great-great-grandparents, Benjamin and Chati, which you can see over there at the top. And this is kind of like it's a slim version of the relationship between me and Edie. And this is great. What that tells us, the DNA that we share, Edie and me, is the DNA, pieces of DNA of Benjamin and Chati that we both inherited, that was passed down to us from this couple. We both have some DNA left from these ancestors of ours. And when I'm looking now at the shared DNA that I have with Edie, and with Edie I have 10 segments, again on 1.9% or something like that. What that actually tells me, these 10 DNA segments that we share are remainings of Benjamin and Chati. These are pieces of DNA that we carry with us, of theirs. And this information is important because we can leverage now this information and use it to look at other DNA matches as well. And let's see how we do that, how we can leverage the information that I just learned. So after I figured out that me and Edie are related, and these are our common ancestors, I have a second cousin once removed from relatively far away, who I was able to identify. And I know that the DNA that we both have is of Benjamin and Chati, how we can take that information and use it even further. So another DNA match that I had, he was there, I think, even before Edie, and we were never able to understand how he's related to us, is a guy named Melvin. And I wanted to see whether now that I know how Edie is related to me, whether that can help also solve the Melvin mystery. So I went again to the Chromosome Browser, and I chose to compare the DNA between myself, Edie, and Melvin. And this what came out. So we have one triangulated segment, which is great. That indicates that Melvin is probably also related to me on the line of Benjamin and Chati over there. Maybe they are not the common ancestors of the two of us. Maybe it will require jumping another generation up, which in this case it did. But that is the direction I need to take. So look at how much, like, I don't need to go through all of the research again to look at, to understand how Melvin and I are related, because I have that reference point, right? I know how Edie is related to me. I figured that out. So now I can use that information and take DNA matches who share maybe not a lot of DNA with me, or less segments, in this case 7, and I can maybe try and understand how they are related to me based on the connection that I know to Edie, to my anchor, to my known relationship. And this is why in many of the cases it's called cousin matching, because we're trying to take people from different sides of the family, as many cousins as we can, because they help us take the decision of going right or left paternal or maternal, when we're climbing up the family tree and we're trying to decide whether a DNA match is related to me on the paternal side or the maternal side. So if I have a cousin, for example, up till this day, I can't really say if the 10 segments I have with ED, which I have inherited from Benjamin and Hati, is this Benjamin's DNA or Hati? And maybe some are this, and some are hers, and some are his, because I couldn't find yet a connection that can help me break that down. If I'll be able to find a cousin of a descendant of cousin of Hati and test her, and I look at the triangulated segments, I look at the segments which I share with her and I share with this couple, I'll be able probably to break it down and say, okay, so if now I see that there are only 5 or 4 out of the 10, these 4 came from Hati and these 6 came from Benjamin, for example. So this is why testing many cousins can really help. So we were in the Melvin example, and we saw that there's one triangulated segment, which is right here. And this is great. Again, it saved me a lot of time, and I know that me and Melvin are related through Benjamin and Hati. This is the direction I should follow, as we saw here. Because Melvin also has a piece of DNA that was inherited, an IBD segment that was inherited from Benjamin and Hati, from one of them. We don't know who. But there's something even more interesting here. Aside of the one triangulated segment, which is shared between myself, Edie, Melvin, my mother, my aunt, my grandfather, we all have that piece of DNA that was inherited from that couple. Melvin has 7 shared segments with me. And now, these segments right there were also inherited by Benjamin and Hati. Because I didn't know about this segment up till now, right? Otherwise, I would have seen a triangulation on that area as well. And the reason is that Edie just didn't inherit the DNA of Benjamin and Hati in that specific spot. She inherited from the other side of the family, from the spouses, or from a different grandfather or grandmother. But it's not Benjamin and Hati's DNA over there. But Melvin can indicate additional information. He can contribute more DNA when I'm trying to build a map or to better understand how DNA matches are related to me. What we're doing here with the segments is that we're trying to map them. And I'm sure some of the people are familiar with the concept of DNA painter. And that's exactly what it is used for. So you're trying to take your DNA matches and create yourself a map of saying, that piece of DNA that I have right here was inherited from these couple of ancestors. And you can, by doing that, you can look at the shared DNA that you have with other DNA matches. So for example, if now I'll go and I'll try to compare myself with Melvin and another guy, and we'll see on chromosome 2 right there where I'm highlighting the orange color that we have a triangulated segment, that's an indication that the new DNA match I'm currently looking at is probably also related through Benjamin and Hati, but using segments that I didn't get from Edie. Edie didn't indicate that information is coming from Benjamin and Hati, and there are 7 additional segments here. So this is really the power of segments, of shared segments and triangulated segments, is by trying to look at groups of DNA matches, is how the information that you get from each DNA match when looking at shared segments can contribute to the understanding of which parts of the DNA were inherited from different ancestors and how your DNA matches are related to you. You can break them down into groups just by looking at the triangulated segments and building kind of like hypothesis or directions to research, and it can save a lot of time. Because here, for example, I've saved myself, I don't know how many decisions of left or right or paternal, maternal I had to take, and I automatically now know that Melvin is related through that side of the family. I might need to go up the tree, go a few generations up, but that's definitely the direction I should pursue. And that opens up a window with for many more DNA matches to understand how many more DNA matches are related to me. I just need to look for those who also match myself and Melvin and triangulate at this specific spot. And that's an indication that we're all related through the Benjamin and Hati line in my family tree. With that, thank you very much. There is a lot more to talk about segments and more capabilities and building a map of segments and information. But I hope that was kind of a good intro that explains maybe some of the basic terms that you've heard in the past of what are segments, why does it matter whether we should look at them or not. So I hope I was able to shed some light on these. And I thank you all very much. And back to you, Jeff. Thanks again.
And thanks to Ran. I love learning from him. Jana writes in saying, Ran is so good explaining complex issues so simply. Just love listening to him. And June says her mind is blown away. She's looking forward to watching this again. Well, and Nancy says it's the best explanation yet of segments and SNPs and centimorgans. And wow, wonderful comments coming in from so many people. Thanks so much. And now, by the way, if you want to learn more from Ran, I've got his page here on the screen, and I'm going to copy this link up here, and I'm going to put this in your chat area. And there you go. So some of the other classes that Ran was talking about would be found right down here. So this is where you can go and learn more from him. Okay, let's do this. Our next MyHeritage webinar that will be live will be coming up on May 12th by Jim Beidler on leveraging MyHeritage's German resources effectively. And we'll do door prizes. And our first door prizes is going to be a 1-year MyHeritage complete plan. And we're going to give this away to Helen Shimmick. Helen, congratulations, and this is coming your way. And then we're going to do a MyHeritage DNA test kit, and we'll give this to Mary Russo. Okay, thank you. Now, because Ran is, like we said at the very beginning, Ran is not with us live, we're going to dispense with any questions and answers time today, and just let you get up to MyHeritage, either upload your raw DNA from elsewhere into MyHeritage, and you'll be able to begin viewing your matches within a couple of days usually, or go and explore the Chromosome Browser as he is shown here today. And by the way, I was just checking to see if you noticed this, which a couple of you obviously have. Let's switch this back up here like this and conclude with my correct slide. All right, everybody, it's been very enjoyable. I hope that you've learned a little bit about DNA today and that you can apply this to your own personal research. And we'll see you next time. Thanks, everyone. Bye-bye.